But I'm going to talk specifically about Pacific Northwest forests. And I would define this as sort of running to the west of the Cascade Mountains up through British Columbia, including the Douglas fir, western hemlock, western red cedar zone, but not the drier interior of British Columbia. And it can apply, I guess the concepts can apply to Alberta, but I'm not going to talk about Alberta forestry at all. Okay? And in terms of why I'm here, well, I like your weather. You know, actually today, this is Seattle, and we rarely get any sun during the winter. We usually get rain, cool, but not super cold, but no color, no light, just on and on and on. Rain events that aren't very intense, but they can occur for months at a time. So welcome to visit Seattle and the University of Washington, but now is not really the time you want to come there. So I look at this area, you know, Edmonton, Alberta, and you've got 3 times as much sun as we do right now. So that's why I'm here. Okay, it's because I needed to get a little sun, and I have been getting a lot of it. I've been outside for the last 5 days. We had an interesting table last night at the seminar. Yeah, and there were 3 mule deer hunters there, and then there was Scott and the new professor from Panama. Yeah, there, and they didn't have a clue about any of it. But that's why I'm so red, is I've been outside a lot, and it's been really, really enjoyable. I love this region. Last year was a little different when I got here. This is what it looked like after I drove through it for a while. So Edmonton can get some pretty intense weather, I guess. You had a little bit of it, but that was something else. And it took a while for the road crew to catch up. So I didn't come up here for to see snow. I came up here to see sun. The speaker last night, Norman Uphoff, I managed to miss the seminar, but hearing him talk at the dinner, I did a little research on, I'd heard a little bit about what he's talking about. And in some respects, this is the idea of getting away. A lot of what we've been doing in agriculture and in forestry has been more and more use of fossil fuel energy, okay, to increase yields, and also to get away from human labor on the farm and in the forests. And a good example of that is me. My family goes back to the 1600s in what would become the United States and what would become the state of West Virginia eventually, but wasn't back then. And they were all farmers, generation after generation after generation. Given where they farmed, all very poor, eking out a living, not a whole lot of time to do much but farm, and maybe a little bit of recreation, but always thinking about where food was going to come from. I'm the first generation that wasn't a farmer. My father was for a while, but then he decided that this wasn't an easy life. And then I've not farmed at all. I've got a nice garden. I do all this. I like to hunt and everything. But I'm very reliant on the food supply from our current agricultural production system. And in terms of forestry, from our current forestry production system. Norman has talked a lot about trying to utilize not so much all the materials we can create from fossil fuels and energy, but going back to a system that's a little bit more natural. Not eliminating that, but utilizing it a bit more wisely. So it was really interesting to read about this, and a lot of it makes sense. And interestingly enough, we've been focused on one of the central aspects of that for pretty much for the life of soil science and forestry applications, and that's the nutrient cycle. Utilizing the nutrient cycle, not only having inputs into the system, but relying on what's in the soil, managing that, and then putting inputs in possibly where you need to or where you want to increase, and then also in the case of a nutrient like nitrogen, possibly relying either on natural inputs and not exceeding that, or actually manipulating the system with natural things like red alder, which fixes nitrogen in the frankia in the root systems. So this kind of picture, this is about, I believe, 1962. This is more than 50 years old, right? And this is a picture of a Douglas fir nutrient cycle that was created in a stand many, many years ago. And a lot of what we work on is focused on this kind of a picture of forestry in terms of its sustainability. Now, I'll switch quickly about what's driving my research now. It isn't so much the production of wood for building homes and things like that, or for paper. That's a pretty established industry. That's very much part of the state of Washington, very much part of the state of British Columbia and Alberta. It's an important industry. Okay, I'm focused more on energy, and right now we, the United States and Canada, gets most of its energy from fossil fuels, and that's not going to change dramatically, at least in the near future, and it may not change in the relatively far future. So here's the current, pretty close to current energy situation. The last time it was done and published, year 2000, the U.S. with 5% of the world's population uses a quarter of the world's energy, which could be embarrassing or awesome or whatever way you want to look at it. Unfortunately, the world is looking, Canada's right up there too in terms of per capita consumption. The world is looking at us as their model of where they would like to be. We have many students from China, for instance, and China and India and other populous countries use a tiny fraction per capita, but are increasing their consumption of energy. So the U.S. uses about 100 quadrillion BTUs of energy, and I'm not sure what that is in terms of joules or whatever, but the key here is that about a little less than 3% of that energy comes from biomass. A little less than 3% comes from hydroelectric, and then all these other systems are tiny fractions. If you drove through eastern Washington, you would think we generated all of our energy from wind. If you drove through the Midwest with the windmills up in the air, you would think all of our energy came from wind as well. It's very visible, but it's a very tiny amount of the total energy. It could possibly increase. And our goal right now is to increase this, okay, which is a renewable resource and doesn't contribute to global climate change, increase CO2 the same way that a fossil fuel like coal or oil or even natural gas does. So I've been part of the evaluation of the potential of biomass in the United States for energy, ranging back for what we call the billion-ton biomass study to the current one. And I was on these panels, and we're estimating that right now the U.S. could capture about 1.5 billion tons of biomass material per year that could be on top of what is already utilized to use as either producing energy or possibly as a raw material for chemical industry, for instance, synthetic fuels. Here is the numbers associated with the projections we had in that latest study. Our current use of biomass, these are million dry tons per year and currently used feedstocks. And then what is projected as possible over time with economic and technology models. Okay? Our technology for recovering these things tends to improve with time. Cost, for instance, you can produce a lot more biomass if you're willing to go in and take out every little bit material, but that's not very practical. So this is forest sources. We can possibly double those. Agricultural sources already highly utilized. Okay? So the estimate for increasing agricultural resources is much smaller. Here's a graph that shows what this study estimated we could potentially produce from different sources. And these are just two of the possible sources. So forestry does represent a substantial potential for increasing the utilization of biomass for bioenergy. It can be used, this material, for instance, is left over after a commercial forest harvesting in western Washington. There's an enormous amount of biomass here, almost as much as was taken out with the logs. Okay? Of course, most of the carbon resides in the soil in these systems. So it's a relatively, hopefully, a relatively stable component, but not entirely so. And we wouldn't be recovering soil carbon, but we can recover this potentially depending on the economic market. Okay? And the idea is that this could be burned directly for electricity, or it could be, we could use the cellulose and some of the chemicals that trees produce to produce biofuels. And if you think about cellulose and plants, what's the very first thing that plants do in photosynthesis? What's the very first chemical that they produce before they make cellulose? First question of the day. In photosynthesis, plants produce glucose. Awesome. A plus. They produce glucose, and then that is synthesized into more complicated molecules. So what we can do is we can break those back down into glucose, and then how do you turn glucose into a biofuel? Or beer? Or fine Canadian whiskey? Yeah, you can use a simple system of fermentation. And in fact, I work a lot in Brazil, and they produce the bulk of their transportation fuel, at least in cars, not so much in trucks, from sugarcane. It's a well-developed industry. It's pretty much standing on its own economically, and it's completely renewable as long as you can continue to produce sugarcane. So these are some of the potential sources that we can have for raw materials for a bioenergy or a biofuel. And this material right now in Western Washington can be a problem. It can be a source of insect infestation, depending on the particular circumstances. Obviously, it can be an enormous problem with fire after a forest harvest. So what I'm going to evaluate, what we're going to talk about now, is whether or not this material can be taken off, whether it will cause a problem with nutrients such as nitrogen, or whether it can be done sustainably. Visually, if you take that material, it's obviously going to be a very different condition. Okay? So here, for instance, there isn't a whole lot of this currently being done. This is one example in eastern Washington in particular. It's almost a different state. It's kind of like BC versus Alberta. We have a mountain range right through the center of the state. And a number of schools have projects now where this kind of material is collected from the forest, and this is an enormous problem with fire. Okay, fire can really devastate these systems. So what they do is they collect this, they haul it to a central place, they grind it, and then it's fed into the furnaces. Furnaces can be retrofitted that currently burn oil or natural gas to burn this biomass. So this material can be taken out of the forests. Here's an example of what would be done. This can either be ignited and burnt, which is where most of it goes because it's a tremendous fire, an insect infestation hazard, or it can be collected and utilized. And there's been a number of evaluations of the amount of material that can be produced in a typical forest harvesting. Okay? Here's, for instance, an example of a current steam plant in the state of Washington. This is the Columbia River as it comes out of BC. And this is not a whole lot of energy, obviously, but it's a very important source of energy and also jobs and employment for a very poor region of the state of Washington. Okay? And the idea would be to have these kinds of facilities that can convert biomass into an extremely utilizable form of energy, electricity. We can even potentially use electricity with the advent of battery energy, the new battery technology. A lot of people in Seattle now are buying, there are 3 different cars right now. One's made by Nissan. It's a Leaf. The car, I think that's the most popular. There's also a Ford, and then there's a really, really expensive sports car that I've only seen one of in Seattle. But potentially this could also be used as a transportation system. It's just that you're not going to be driving from Seattle to Edmonton on battery power anytime soon. There was a equivalent facility that was going to be located in western Washington. This is in eastern Washington. And all the blueprints were done. A lot of the work was done. I helped evaluate the potential for the supply of biomass for that. This is actually taken from the paper. Obviously, they're not going to burn that, but they would burn other material. And that was stopped. A number of things, but one of the major problems was the availability of raw material to sustain what that plant needed. So we may revisit this in the future, but ultimately the Forest Service refused to provide any biomass, and the state of Washington Department of Natural Resources refused to promise any biomass. So with the matrix of land ownership, it just didn't pan out economically. They would have had to haul the biomass distances that were too long. So the company backed out of it for now. Air grant, Scott mentioned the $40 million grant. This is driven by a strategic need of the United States, which is aviation fuels. Okay? You can't fly planes with batteries. Cars don't even do very well with them. You need a very high energy, compact, in this case, flyable energy source. And that would be something, right now it's almost entirely made out of petroleum, jet fuel. But we have had experiments where materials have been synthesized and added to jet fuels at rates, I don't know, up to 10% or so. And that works very well. So the idea of this grant is it will start producing some of our jet fuel from biomass. Okay? Currently, the United States, 10% of our auto fuel is alcohol that's mixed in with gasoline. And I understand that Canada also does that, even though you've got abundant petroleum resources. Okay? There's a couple reasons for this. It helps diversify the fuel source. And it also, this material doesn't contribute to carbon dioxide in the atmosphere the same way that fossil fuels do, like oil. Okay? So I'm part of a $40 million grant that's to Washington State University. There's about 100 PhDs working on this. I'm one of them, and I have about a proportional budget over 5 years. And then there's also $40 million, these are 5-year grants, to the University of Washington, which the PI is right down the hall from me, but I don't work on that particular grant because they're utilizing hybrid poplar as their main biomaterial to produce the biofuels. So I'm going to talk a little bit about some of the evaluation I've done. My job for the WSU grant is to evaluate the sustainability of different systems of producing biomass that would be used to produce aviation fuels. And if you produce aviation fuel, you also produce fuel that can be used in cars and trucks and things like that. So it's a very versatile material. And the main problems that we have, the idea of Air Grant is that we already produce extremely high value material that's used to build houses, to make paper. We don't want to rob that material out of the economy. We want to continue to produce boards. We want to continue to produce plywood. This is also a big part of Alberta's economy. You produce some phenomenally highly valued timber that a lot of it's exported into the United States. Okay? So that helps sustain jobs, helps sustain an economy. And I guess it's one of the reasons why the tuition at the University of Alberta is 1/4 of what the tuition at the University of Washington is. So you can kind of thank the economy. You have a vibrant economy here. Ayers is a little worn. It's still very strong. But we're having problems sustaining things like higher education in the United States. But we've evaluated, and a couple things we've come up with is that maintaining the organic matter in the source, which contains a lot of nutrients, contains cation exchange capacity, ameliorates the destruction of good physical properties of soil and also chemical properties. Maintaining organic matter in the soil, not losing it, is a priority. And then also, reduce the porosity of the soil. In particular, if you reduce it such that the soil doesn't aerate well or doesn't hold water, or water runs off, then these are also potential problems. And so we have a network of studies that are designed to evaluate these. And I've been involved primarily with the Fall River and Matlock in Washington, and also the Molalla study in Oregon. And then this network extends through the main forested areas of the West Coast. You'll notice that there's not really any in our central parts of the United States. And then the southeast, the southern pine, loblolly pine / pine region, which is where most of the wood in the United States is produced. And then a large number in the northern region of the United States as well. Notice also that we have studies in Ontario and BC, but I think maybe one is, they're very close to Alberta, but it's sort of nestled up against the Rocky Mountains there, so they don't come over into the province of Alberta. These are what we call long-term soil productivity network studies. Okay? And the idea is that if we had a typical normal harvest, we would leave, this by the way has been harvested, planted with Douglas fir stock, and these are a few years old. So you see this material here is left behind in current systems. Sometimes if there's an excess amount of it that would interfere with the planting and survival of the seedlings, we'll remove material enough to get it to where we can have good survival. Okay? And then this would be possibly an alternative where we remove a lot of this material and turn it into jet fuel, aviation fuels, or for the particular study that I'm involved in, or it could also be used for other kinds of bioenergy. So CO2 in from the atmosphere, biofuels out. No net impact on global CO2 except as the amount of CO2 carbon stored here changes, or the fossil fuel that's used to make the harvest and so on changes. And it's phenomenally better than pumping oil out of the ground, fossil fuels. The amount of fossil fuels to produce equivalent amount of energy here is substantial. You've probably seen the corn evaluation. You're not producing an enormous amount of energy relative to the amount of corn. There is a net production of energy, but this is much higher. Sugarcane is also quite high. Alternatively, you may need to put things into this system. We can fertilize. We often don't, but in many cases we do. But there's a substantial amount of diesel fuel required. And if you're producing things like herbicides and fertilizers, these typically are produced with fossil fuel energy. But they don't have to be. We could produce those. We could produce nitrogen, for instance. Right now it's commercially produced with natural gas to produce hydrogen, and then you force that together, high energy and pressure, to produce ammonia. We can do that independent of fossil fuels, but right now commercially that's the main source. The valuation goes something like this. It's an ugly slide, but it has the data. If we look at the biomass, and this is the merchantable part, the part that's typically taken off in a forest harvest. This is the branches and the needles, and then the stumps and the roots, which are typically left. We get, in this case, about 400 of a total of about 600 megagrams per hectare, okay, in this harvest. However, if we look at nitrogen, that 400 out of 600 only contains, that's about 2/3, okay? It only contains about 20% of the total nitrogen. And if we harvest the branches and the needles, we greatly increase our removal of nitrogen and other nutrients like phosphorus, potassium, and calcium relative to the amount of biomass we get. And that's because the interior woody part of a tree is almost devoid of nutrients. It's almost entirely carbohydrates. Very few nutrients are stored there. The nutrients are high in concentration in the meristematic material, particularly in the foliage and anything that's growing. So, in the case of Douglas fir, in the Pacific Northwest. This is their source of biomass. Okay? We have identified situations, many, many, where nitrogen limits growth. Okay? And we do have lots of response to nitrogen fertilization. Okay? We've also identified a number of situations where they don't respond and or there's an excess of nitrogen. There's a lot of nitrogen that's been stored over time through natural inputs. And what we want to know is whether or not we can identify stands that would be problematic with this additional removal versus stands that are resilient to that removal. And this is the generalized risk strategy that we're using. And we have not found any examples in the literature, in research, where if we follow this, we would have imminent decline when we assess it as a low risk. So what we do is we look at the total ecosystem pool. That would include the vegetation, understory, roots, everything in the living material and the dead material, forest floor, and then the soil resource. And we'd evaluate the total amount of, for instance, nitrogen. That's the one I'm going to use because that is the main limiting nutrient in our region, not everywhere else in the world. If we remove less than a fraction of 0.1 or 10% of the nitrogen, we have a very low risk of reducing the productivity of the next stand, the subsequent stand. If we start to get up to 30%, then we have a serious risk. And this has been borne out in some studies, but it's a variable. If we start to remove half of the total ecosystem nitrogen, then we have a serious risk. We're really fairly confident that we're going to have a decline. That's what we don't want to see. So we use this system to evaluate, in one case, one of those long-term ecosystem studies, the Fall River. And here we have the biomass, the carbon, it's about half. Biomass is about half carbon. And all the different ecosystem components, the roots, the soil, and so on. And then we do an in-rest rating. So remember, it's 0.1, 0.3, and 0.5. So if we have a bowl-only harvest, there's very little risk of the loss of so many of the ecosystem nutrients that would be detrimental to the next stand. We add the material, we about double the amount of nutrients, but we only increase the biomass a bit by removing those branches and needles and so on. And in the case of adding stumps, we're still not up to 0.1. So if we could even potentially remove the forest floor, not suggested. We don't want to do this. This is just for an evaluation. And then if we wanted to go in and remove the roots. So this represents an ecosystem that's probably very resilient to the additional removal of forest biomass for whatever use, bioenergy, for instance. By the way, you're going to put these on. These will be online, so you can go back and get them. That freely show them to all your friends and your parents or whatever. It's all material that you can use or whatever, and it'll be available. In the case of another study, of Matlock LTSP, which is also in Washington. So Fall River came out somewhere in a very low risk. But it's a different story. The soil pool is not as high. And when we start removing, we start to see we're still not up to a serious risk, but this is a whole tree harvest, all the above ground material for Matlock. So you can see all sites are not the same. That's really, really important. Just look at the soil here and you can see, oops, wow, I really backed up, didn't I? You can see the Fall River soil and the Matlock soil, much rockier, much lower in nutrients. And so I want to just talk about a larger scale study. We have a regional study where we're going from northern Vancouver Island down to southern Oregon, and we've quantified the ecosystem nitrogen, carbon, and other nutrient contents for 73 different sites. And these are the ranges as we go from, this is just by latitude. So northern Vancouver Island, down through Washington, down to southern Oregon. And what we see is Well, a fairly poor site, about 300 kilograms of ecosystem nitrogen in one site in Vancouver Island, and 25,000 kilograms per hectare in one site. I believe this was in Oregon. Okay? So that's almost 100 times difference. So you can see these sites are not all created equal. And so this is the range of this particular study in our evaluation. Okay? Red being glacial origin soils, green being sedimentary origin soils, and then everybody has a little bit of volcanic input, whether it's from our own volcanoes or it's from volcanoes over, like in Japan and so on. But we have a substantial amount of igneous input into many of our soils as well. And what we did was this was a fertilizer study. We're trying to assess if we can tell whether or not a site would respond because of its site characteristics, altitude, latitude, soil. But what we did was we wanted to do an evaluation of the nitrogen removal and evaluate it. So our stands were about 20 years old. So we needed to grow them to a harvestable age. We did that with a model called Organon. Okay? And then we distributed the biomass. We distributed nutrients onto the different parts of biomass using Jenkins and Augusto equations. Okay? So we have a lot of assumptions. These are not existing stands. These are stands we're projecting into the future to a harvestable age to evaluate the nutrient removals. And then we use this stability ratio. Less than 0.1, low risk. 0.3 is when we start really getting worried. If it's greater than 0.5, we should not be doing this. Or we can come back and apply the nutrients. And here's the basic evaluation. Here's the harvest export of nitrogen. And then here's the total ecosystem nitrogen store. So this goes up to about 25,000 and as little as 300. Okay? The red line is a bowl-only removal, removing the stem and the bark, which is a typical harvest. Oftentimes, a lot of the bark gets broken off, sloughed off during the movement of the material. So this would actually be a worst-case bowl, commercial harvest scenario. And then these blue dots are if we add the branches and the foliage to the harvest mix. So we produce more biomass, which could be used to produce aviation fuels. And the green line is the 0.1% stability ratio. So anything that falls on the right of this line is a low risk. Anything that falls left of it should be looked at further. And then the 0.3 line is if if we're above that, then we're really worried. And you notice that some of them fall above this, okay? Fall above both lines. So these are sites that we probably should look at further. Now, these growth projections are a little bit questionable. They may be a little bit optimistic in terms of the growth of the trees. This is the current Fall River bowl-only removal at whole tree harvest. So the projections with the model may be a little high, and thus the biomass removal is a little high. These were projected to 50 to 55-year rotation lengths. The Fall River was harvested at 47 years, so a similar age. But I think that between the way forests develop, I think the models may overestimate the ultimate productivity. On the other hand, Fall River is not the same as these stands. These are highly managed, well-stocked stands. They're what industry considers the optimum kind of stand. And then another way of looking at it is this is the percent of the store that's removed with the bowl-only removal. Okay? And you can see that it drops down very, very low when we start to get out the very high nitrogen levels. And this is with the total tree removal. Okay, this is a risk map. It's a homogenized data, Krieg. It's probably not a good thing to show, but I'm showing it anyway. And what this is it shows the percents of nitrogen removed. And it's no real surprise. The British Columbia sites tend to have relatively low total site stores, and the Washington and Oregon sites tend to be more rich. And that's just borne out with our data. So when we start removing trees, we get a little bit more risk in these soils that have lower nitrogen stocks. But in not all cases, we have a paucity of data in BC, but in some cases we had relatively rich sites. So again, all sites need to be evaluated individually. Probably these regional evaluations aren't so great. So we think we have a relatively low risk of depletion when we remove additional material. In general, we're using these levels with the whole tree harvest and this level with the stem harvest, stem-only harvest, as very indicative of very, very low risk. There's other factors that go into play. We didn't evaluate them all. It would be an enormous study. But the sites are not all the same. There are some that we would question. Whether or not it's actually a problem remains to be seen because we didn't actually evaluate that. We'd have to harvest the stand, and then we'd have to replant it like we did with the long-term site productivity studies. We put this regional evaluation into place for a few thousands of dollars into an existing study. The Fall River long-term site productivity study has already cost about $6 million. One site, one location. And we did this for 73 sites. So we're not able to do the ultimate evaluation, which is the growth of the new trees on these sites. And then finally, fertilization is a viable tool. Okay, there's some things we didn't do with this study, other nutrients. We also sampled the soil depth to a meter. Some of these soils seem to be quite a bit deeper than a meter. And although we probably can't, these things we have yet to evaluate, one of the things we did was we evaluated 26 of the sites down to as deep as 4 meters because these seem to be deep. Has anybody ever studied in a tropical area and dug deep into a soil anywhere? Has anybody ever dug below a... Okay. Well, I was in a pit in Brazil, 12 meters deep, and there are roots down there. And these redistribute water and probably nutrients. And it's very hard to study. How deep did you go?
We went down to about 3 meters.
Yeah. And who dug the hole? Graduate students? Yeah, it's a whole order of magnitude different. We did this with the backhoe, okay? And you can see the depth here. And then interestingly enough, this is the distribution of nitrogen we got. And it's not consistent. It's different with some sites, okay? So for instance, here's where our forest inventory and analysis, which is our national program to understand the ecology of our forests. They sampled a 20 centimeter soil depth. The European system to understand soil ecology samples to 30 centimeters. And then here's the nitrogen profile. And in many cases, they tend to level off, but they're always increasing a little bit if the soil actually is that deep. Obviously, not all soils go down to multiple meters of depth. But look at this soil. You would evaluate that it had about, 2,000, 3,000 kilograms, but it has 25,000. And much of that is deeper. And this was a soil that had been built up with apparently multiple events of volcanic eruptions over time. So deep in that profile, there was a substantial amount of buried horizons, I think. And that's why it just keeps increasing. And then some things that kind of defy explanation, but I'm sure there's a story here. So the net impact of this, the take-home message, is that the soils are different. And we need to study soils as individuals and not lump them all together, although we're naturally probably going to do that. One more thing. Challenges. This only looks at part of the picture. There's a lot of things we don't know about. Here's a nice even-age stand in British Columbia. What's happened here? Mountain pine beetle, yeah. So even the best laid plans of people, sometimes things happen not quite the way you want them to. There's a lot of other variables that would go into this picture of biomass production. I just did a ecosystem evaluation of nitrogen only. It's only one thing. But it is an important thing, a critical thing. And these are all the different people that have funded one part or another of these studies. And thank you all for bearing with me. And I hope I was able to explain a little bit of one part of the critical evaluation, the potential for using air forests as sources of bioenergy and biofuel.